Alright, so in this video, I'm going to be explaining another important article with the title Learning to Generate Novel Domains for Domain Generalization. This paper in 2020. This paper focuses on domain generalization, the task of learning from multiple source domains, a model that generalizes well to unseen domains. A main challenge for domain generalization is that the available source domains often exhibit limited diversity, hampering the model's ability to learn to generalize. We therefore employ a data generator to synthesize data from pseudo-novel domains to augment the source domains. This explicitly decreases the diversity of available training domains and leads to a more generalizable model. To train the generator, we model the distribution divergence between source and synthesized pseudo-levered domains using optimal transport, maximizing the divergence. To ensure that the semantics are preserved in the synthesized data, we further impose cycle consistency and classification losses on the generator. Our method outperforms current state-of-the-art domain generalization methods on 4 benchmark datasets. This is the motivation of our approach. We improve generalization by increasing the diversity of training domains by learning a generator network G to map images of source distribution to a novel distribution. We then combine both source and novel domains for model learning. Overview. So in A, you see that the conditional generator is learned to map input to a novel domains whose distribution are drastically different from the source domains, while keeping the distance between the novel domains as far as possible. In B, you see a cycle consistency. By the way, there is a paper called Cycle GAN, similar idea I've seen there as well. So a cycle consistency loss is imposed on G to maintain the structural consistency. And C, you see the cross-entropy loss is minimized with respect to G using a pre-trained classifier for maintaining the semantic consistency. So B is very important because it's a cycle consistency loss. We want to have good structural consistency. And so you see A and B are just source domain labels, and the red one are just the novel domain labels. So we are provided with K sub S source domains with indices 1 through K sub S. The goal is to learn a model which can generalize well on unseen target domain. We learn a conditional generator G that maps a source distribution to a novel distribution by conditioning the novel domain label K tilde. So P denotes an empirical distribution rather than the real distribution, which is inaccessible. In practice, we use sample mini batches X sub K instead of the full empirical distribution. Therefore, the domain translation function is defined like this. For each training iteration, we randomly sample for each source domain K a mini batch, which is transformed to a randomly selected novel domain K tilde. This is our novel domain K tilde. And the objective is to force a novel distribution to be as dissimilar as possible to any source distribution, thus creating a new domain to augment the existing source domains. So this D is the distribution divergence measure. And this equation will be summed over all source domains K, and each independently draws a novel domain label K tilde. In addition to maximizing the difference between source and novel distributions, we also maximize the difference between the generated novel distributions. So K tilde 1 and K tilde D are in D sub n, those novel domains. When we say D sub n, it means those novel domains. And the diversity constraint diversifies the generated distributions, ensuring that the model benefits from generating K sub n novel distributions. The model so far is optimizing a powerful CNN generator for the novelty of the generated distribution. This produces diverse images, but may not be preserved their semantic content. So similar to that idea in cycle GAN that I said, we are minimizing this one. We want to be consistent. G of G should be X. G of X should be X. Because it's like a reconstruction loss, where the outer G aims to reconstruct the original X sub K given as input the domain translated G and the original domain label K. Both G's in the cycle share the same parameters. And then the rest of that is standard just to maintain the category label, enforce semantic consistency. We further require the generated data is classified into same category as the original data. So we have this cross entropy loss. So the full training objective is just loss of novelty, loss of diversity, this cycle consistency, and cross entropy. So you see the architecture that left and right images exemplify the forward cycle and backward cycle respectively. And we use the Wasserstein distance, that also called the optimal transport distance, which is the infimum of expectation of their costs from one to the other. It computes the minimum cost of transporting masses between distributions in order to turn P sub A, P sub B to P sub A. We have this transport. And to explain unbiased gradient estimators when using mini batches, we use this generalized squared energy distance. And but W sub C here is the what we call Sinkhorn distance. And we define the cost because C is the pairwise distance, but we have also a cost, the cost between XA and XB, using the cosine distance between instances. And phi here is just the constructed by convolutional neural networks, which maps images into latent space. So we have the latent representations of them, then we have cosine similarity, then we have the cost function. So in practice, phi is a fixed CNN that was trained with domain classification laws. You see the visualization of generated images.